Full adder. In this video, we discuss about the full adder circuit, its basics, and its designing using gates and multiplexer. But first, we should understand why we need full adder. As half adder has only two inputs and there is no provision to add a carry coming from the lower order bits when multi-bit addition is performed. So in order to remove this tendency, we need a full adder. As shown in the diagram, we have only two inputs and we have only two outputs. There is no provision for the third input. So what is full adder? A full adder is a combinational circuit that performs the arithmetic sum of three input bits. A full adder consists of three inputs and two outputs. You can also check in the block diagram. It has three inputs A, B and C in and two outputs sum and C out. Here in the slide we are seeing the truth table of full adder. In the first row you can see that when all the inputs are in the lowest state, the sum and carry is in the lowest state. Whereas in other rows, when one of the input is high, our sum is in high state, whereas carry is in the low state. But when two inputs are in high state, then sum is in the low state and carry is in the high state. Whereas when all the three inputs are in the high state, our sum and carry both are in the high state. Now, if we solve the K-map for sum and carry, we get the sum and carry equations, which is shown in the slide. Here sum is A's or B's or C and carry is A and B or B and C and C and A. If we implement the equation of sum and carry in terms of basic gates, then the diagram of full adder is shown below. Here in this diagram, you can see there is one XOR gate which represents the sum, whereas carry requires two input AND gates which are 3 in number and one OR gate which is 3 input according to the basic equation. Further, we can say full adder can also be designed by combining the two half adder which is shown in the figure. Here, if we consider the first slide, in that slide we see our half adder consists of only one XOR and one AND gate. So if we cascade, if we combine two half adder and we can use one OR gate, we can form the full adder. Earlier in this class, we discussed about the multiplexer and multiplexer designing. Here we also design full adder using multiplexer, which is very important and very interesting for the students. If we check the truth table of full adder, which we discussed above, we know that sum and carry output of a full adder is written as sum equal to minimum term of 1, 2, 4 and 7, whereas C out is min term of 3, 5, 6 and 7, where A, B, C in are the inputs of the full adder and S and C out are the sum output and carry output respectively. Now, first we understand about the sum mapping with respect to the multiplexer. As a general equation of multiplexer of 4 cross 1, we know that Y output is equal to I0 S1 naught S0 naught plus I1 S1 naught S0 plus I2 S1 S0 naught plus I3 S1 S0. Here we declare it as equation 1, where Y is the output of multiplexer and S1, S2 are the selection inputs. I0, I1, I2, I3 are the data input for the multiplexer. As we know, the output equation of sum for full adder is as follows. F is min term of row number 1, 2, 4 and 7, which can also be written as M1 plus M2 plus M4 plus M7. If we solve this equation according to the Boolean algebra, This can be written as A dot in bracket B naught C in naught plus A naught in bracket B naught C in plus A naught in bracket B C in naught plus A dot B naught C in, which is known as second equation. If we compare these two equations, equation 1 and equation 2, we find that our I0 is equal to A, our I1 is equal to A naught, our I2 is equal to A naught, our I3 is equal to A, whereas S1 is equal to B and S0 is equal to C in. So we map the sum for multiplexer. Similarly, the output equation mapping for carry with respect to multiplexer is as follows. Cout is equal to in term of 3, 5, 6 and 7 rows, and if we expand this equation, final equation comes 0 dot B naught C in plus A dot in bracket B naught C in plus A dot in bracket B C in dot plus 1 dot B C in. Let us call it as this equation, equation number 3. And if we compare this equation number 3 with equation number 1 of multiplexer, we find that our I0 is equal to 0, our I1 is equal to 1, our I2 is equal to A, our I3 is equal to 1, and S1 is equal to B and S0 equal to C in. So if we join these lines, you can see the logic diagram for the full adder using 4x1 multiplexer. From the given picture, it is clear that full adder can be implemented by using two 4x1 multiplexer. One multiplexer is used as a sum for full adder, whereas other is used as a carry. This can also be used for designing the full subtractor. Thank you.